Okay, welcome everyone to our last Oz Geometric PD seminar for the year, 2020-22, in case anyone watches in the future and wants to know which year it was. So today, Kyle Broder is going to speak with a very provocative title here, Curvature and Moduli, and some intimations and propaganda. So very intriguing. We'll look forward to hearing it. Thanks, Kyle.
Thanks, Paul. So I gave a similar talk at the University of Queensland, I think about 2 weeks ago, but that was intended for a more general audience. And since differential geometers are here, I can speak about some more of the exciting details. Okay, so we'll start with something I hope is familiar to everyone, which is the Riemann-Koba mapping theorem, which says that if we take a simply connected domain, which is properly contained in the complex plane, then that's biholomorphic to the unit disk. So up to biholomorphism, we have a complete understanding of bounded simply connected domains. Now, the subject of several complex variables, although it begins a little earlier than this theorem, is really kicked off with this observation of Coincare in 1907 that states that the unit ball in C2 is not biholomorphic to the bidisk, the product of the unit disks in each complex plane. So note that both of these are simply connected bounded domains in C2, but are not biholomorphic, so there's no hope of this naive extension of the Riemann mapping theorem in higher dimensions. And so here we have these Hartog's diagrams, which illustrate or give us some indication of what these look like. But one should be careful that each point in this picture, for instance, if we look at this boundary point here of the bidisk, that would be a torus. So you have to take these pictures with a grain of salt. Okay, so there are many reasons for why there fails to be a biholomorphism between the ball and the bidisk. But the main reason I'm going to concentrate on here is due to an additional convexity property of the boundary, which doesn't manifest for one-dimensional domains. So we'll say that a bounded domain is strongly pseudoconvex if for each point on the boundary, we can find a smooth local defining function for which the complex Hessian is strictly positive definite at that point. So the complex Hessian is just the component of the full Hessian, which is invariant under a change of holomorphic coordinates. So it's the appropriate replacement in the complex analytic category of the Hessian. And we'll say that it's merely pseudoconvex if it's merely positive definite or positive semi-definite. So the bidisk is an example of a pseudoconvex domain, while the ball is a strongly pseudoconvex domain. Now, for bounded domains with a smooth boundary, pseudoconvexity and strong pseudoconvexity are preserved under biholomorphism, and therefore the bidisk and the ball can't be biholomorphic. This was certainly not Poincaré's argument, because pseudoconvexity was really only introduced about 20 to 30 years after Poincaré's theorem. Okay. So this discrepancy between pseudoconvexity and strong pseudoconvexity has important implications for the behavior of complex manifolds which fiber these spaces. So we'll consider the following special case, namely of disk vibrations, which I'll understand to be the following. So I'll declare a surjective holomorphic submersion to be a disk vibration if for every fiber, so the pre-image of a point, the fiber is biholomorphic to a disk. And so I'll typically take the disk to be of complex dimension 1. So I could take the fibers to just be bounded domains in the complex plane, which are simply connected. So the bidisk and the ball both are the total spaces of disk vibrations. If I project onto one of the factors, then both will define disk vibrations over the disk. And just to remind ourselves of what we would understand local triviality to mean of a disk vibration, that would mean that for every point in the base, I have a neighborhood such that the pre-image of that under the projection map would be biholomorphic to a product. Now, the bidisk is the simplest example one could construct because it's globally trivial. It's not only locally holomorphically trivial, it's globally trivial by definition, essentially. On the other hand, the disk vibration coming from the projection onto one of the factors with the total space being the ball cannot be holomorphically trivial, not even locally. So there's this old theorem of Roids which tells us that a disk vibration is locally holomorphically trivial if and only if it is globally holomorphically trivial. So if the disk vibration given by a projection onto the first factor was even locally trivial, the ball would happen to be biholomorphic to the bidisk, but we've just seen that that would lead to a contradiction. So if we think of this in terms of understanding the behavior of the disks which are fibering the ball and the bidisk and looking at their behavior, their deformations, the behavior of the disks when fibering the bidisk in comparison with fibering the ball behave very differently. The deformation behavior or moduli theoretic behavior of the disk vibration of the bidisk is trivial. There's really nothing going on. It's as simple as it can get. But with the ball, it has to be non-trivial. There has to be some kind of, there's no local triviality you can impose. Now, understanding this behavior of complex manifolds and their deformations is non-trivial. It's a non-trivial area of mathematics, and it's very difficult even within that field to have a robust mechanism for generating examples and non-examples where the deformation is trivial or non-trivial. This measurement of deformations of a complex structure or deformations of a complex manifold, there isn't a robust mechanism for checking that. And so it would be fruitful to understand this behavior through something like curvature. So for instance, if I have a disk vibration, so this surjective holomorphic submersion P from X to S, can I detect the behavior of the fibers by looking at the curvature of metrics which reside on the total space X? So there's some hope for this, and that comes from actually Romanian geometry, not from complex geometry or algebraic geometry. So to give some indication of why one would expect there to be any role between the curvature and deformations, we'll just remind ourselves of the structure theory of Romanian manifolds with negative curvature. So first, let me make this definition, which Yost makes implicitly in chapter 8 of his book. We will say that a complete Riemannian manifold MG satisfies the unique geodesic property if for any 2 points in the manifold, I can find a unique geodesic which connects these 2 points and minimizes the length functional within its homotopy class. And so one of the key points or key examples is given by complete Riemannian manifolds with non-positive sectional curvature. These are examples of Riemannian manifolds which satisfy this unique geodesic property. So one important corollary of this unique geodesic property is the Hadamard Theorem, which states that if we have a complete Riemannian manifold which supports the unique geodesic property, then its universal cover has to be diffeomorphic to Rn. Now, the argument is quite simple. The universal cover is simply connected, so there's only one homotopy class to work with. And therefore, for any 2 points in the universal cover, there's a unique geodesic connecting them, which minimizes the length. But then if you just write out the definition of the exponential map, you'll soon realize that the exponential map is therefore bijective. But using some basic Jacobi estimate, you can show that if the exponential map happens to be bijective, then it is in fact a diffeomorphism. And so the exponential map will define a diffeomorphism from Rn onto the universal cover.
Sorry, Kyle.
Yep.
Can you say why there's a unique geodesic on the universal cover then?
So if there is a, this is because of simple connectedness. If you have the unique geodesic property.
Yeah, downstairs though.
I'm only claiming, what am I saying? I'm saying if M satisfies the unique geodesic property, right, then you should be able to have one on the universal cover. That's right.
Yeah.
I think maybe your statement of the unique geodesic property doesn't quite capture everything you want to say there, right? So you said for every P and Q, there's a unique geodesic, but I think you mean for every curve joining 2 points, there's a unique geodesic homotopic to that curve. Is that the correct statement?
Yeah. And so that additional property transfers to the universal cover. Is that what we're
right? So any curve, you have a curve downstairs that lifts the one upstairs. And
that's right. That's right. That's a good point. That's thanks, Ben. This is exactly the reason for detailing this in the talk, so I could learn about this way of doing it a little better. Thank you. Okay, so the next theorem, which will be one of the main theorems as motivation in from the Riemannian side of things, is this theorem of Priceman. So if we have a compact Riemannian manifold with negative sectional curvature, then every abelian subgroup will be infinite cyclic. So there are two additional statements here in comparison with the Hadamard Theorem, which is the presence of compactness and a strict sign on the sectional curvature. So just one nice way of proving the argument or proving the theorem would be to take any 2 commuting loops in the fundamental group of M. The homotopy between alpha beta and beta alpha will give us a continuous map from the torus into our manifold. The strict sign on the curvature, plus this theorem of Ills and Sampson, which says that in the presence of sectional curvature being negative, we'll have a harmonic map homotopic to F. So we now have this harmonic map FH from the torus into M. If you compute the Laplacian of the energy density and integrate that, with the divergence theorem, the negativity of the sectional curvature implies the torus maps onto a closed geodesic via this harmonic map. And so these loops that we get from F and the harmonic map in the fundamental group given by alpha and beta will be multiples of this closed geodesic gamma. Now that will be then contained, so these loops generate a cyclic group. They're contained in a cyclic subgroup of the fundamental group. And either by using this unique geodesic property or by showing first that the fundamental group can't have any torsion in it if there is negative sectional curvature, this cyclic group will have to be infinite. So it'll have to be isomorphic to Z. So that will then say that the group generated by alpha beta is infinite cyclic, but since alpha and beta are arbitrary, we'll see that any abelian subgroup of the fundamental group would have to be infinite cyclic. This is the non-standard. This is perhaps non-standard proof. It appears in Jost's book, but I think it's nice to do it via harmonic maps. So we have the following important corollary, which is if we have a compact Riemannian manifold with negative sectional curvature, then it can't be homeomorphic to a product of positive dimensional Riemannian manifolds. So the way to see this would be to suppose that M is a product, say X times Y, so it's homeomorphic to X times Y. Karatan Hadamard tells us that the homotopy theoretic information of M is contained in the fundamental group. So the higher homotopy groups vanish. But then if M is aspherical, or if M has no higher homotopy groups, then the same is true for X and Y. Moreover, since M is compact, the constituents have to be compact. And so that will tell us that the fundamental groups of both X and Y can't be trivial. Otherwise, you would have a contractible compact manifold, which we cannot have. So in each of these fundamental groups, pi1 of X and pi1 of Y, we have these non-trivial elements, gamma X and gamma Y. Each of these will generate a subgroup. Remember, there's no torsion in the fundamental group, so these will generate copies of Z in each of the constituent fundamental groups. And since they commute, we'll have that the group generated by gamma X and gamma Y will be isomorphic to 2 copies of Z. But now we have an abelian subgroup of the fundamental group that's not infinite cyclic. So this would violate Priceman's theorem. So without compactness, negative sectional curvature does not obstruct products. 2 nice theorems to mention in this direction are given by Anderson and Bishop ONeill. The first result due to Anderson tells us that if we have a smooth vector bundle over a compact Riemannian manifold with negative sectional curvature, the total space has a complete metric with negatively pinched sectional curvature. And the lower bound on the pinching depends on the geometry of B and the topology of the bundle. There's also this result of Bishop ONeill, which tells us that there's a complete metric of constant negative curvature on the product of R with any compact Riemannian manifold with a flat metric. So for instance, a torus. And so we're seeing this continuous interplay between compactness, the topology, and negative curvature. There's really a balancing act. Okay, so we want to see how this carries out in the complex analytic setting. So we'll just remind ourselves that an almost complex structure on a smooth manifold is an endomorphism of the tangent bundle which squares to minus the identity. So not only do we have a smooth map on each of these tangent spaces, but it's actually coming from a map on the bundles. Now, a nice example of such a structure is given by identifying the two-sphere in R3 with the space of unit imaginary quaternions. In that way, this is how we get the cross product on R3. And so with the cross product, I can define an almost complex structure on the two-sphere by identifying each point with a map, identifying each point on the two-sphere with the vector, corresponding vector in R3. This will point outwards. And then I take any tangent vector to the sphere and cross product with that vector, I'll now get a rotation by 90 degrees. And so this will, of course, for each point, give me one of these almost complex structures, but it's coming from an ambient structure on R3. So it's, of course, going to come from the bundle. So this will give me an almost complex structure on S2. Now, in general, the existence of an almost complex structure is not sufficient to yield local holomorphic coordinates. The category of almost complex manifolds and complex manifolds is distinct. There's an obvious obstruction. It's obvious once you've thought about it for a long time, which is that suppose for the moment we have a complex manifold X with local holomorphic coordinates z1 through zn, centered at, say, a point P. The tangent space to the complex manifold will be the complex vector space given by the span of the coordinate partial derivatives, which we view as tangent vectors. On the other hand, if we start with a smooth manifold with an almost complex structure, then the condition that the almost complex structure squares to minus the identity splits the complexified tangent space. So we tensor the tangent space with a copy of C. It will split that vector space into eigenspaces corresponding to I and minus I. Now, if we let x1 through x2n be smooth coordinates on M, and by the definition of eigenspaces, we'll see that this 1, 0 tangent space is spanned by these vectors partial xi minus I j partial xi. And similarly, this 0, 1 tangent space will be spanned by partial xi plus I j partial xi. So what we would, if we were to have a complex structure coming from an almost complex structure, we would need to be able to find a complex manifold which has its tangent space at each point spanned by these 1, 0 tangent vectors. So we've actually seen this idea before. We see this in the context of vector fields and integral curves. So if I think of having a vector field assigning to a tangent vector at each point, we can ask whether we can find a curve which passes through, which glues these together. So it'll have a tangent vector given by the vector field at each point. And what we're asking for here is a higher dimensional version of that. So if I want to talk about an almost complex structure giving me local holomorphic coordinates, I'm essentially saying I have this distinguished subspace at each point of the complexified tangent space. And I'm asking whether I can find a complex manifold with exactly that tangent space. So this would be a necessary condition. Now, the Forbenius theorem tells us that we can express this in terms of Lie brackets. And so I can express the necessary condition in terms of the vanishing of this Nijenhuis tensor here, this ungodly object. But not only that, there's this famous theorem of Neulander and Nuremberg, which says it is not only necessary, but it's actually sufficient. So an almost complex structure is integrable or gives rise to local holomorphic coordinates if and only if this subbundle is actually an integrable subbundle, or in other words, if and only if this Nijenhuis tensor vanishes identically. So let's give the standard example of a non-integrable almost complex structure. So from the cross product on R3, we produced an almost complex structure on S2. For dimension reasons, it's if you compute the Nijenhuis tensor of this almost complex structure, it will vanish identically. So on S2, we have an integrable almost complex structure. That gives us the complex structure coming from the projective space. But we can do the same thing with S6, realizing that as the space of unit imaginary octonions. And this will give us, in the exact same way, an almost complex structure on the sixth sphere. Now, if you compute this Nijenhuis tensor of the almost complex structure on S6 inherited from the octonions, it doesn't vanish precisely because the octonions fail to be associative. This Lie bracket doesn't vanish just because of the associativity not holding anymore. Okay, so the point of expressing the complex structure in terms of this endomorphism of the tangent bundle is that it makes the compatibility between the complex structure and the metrical structures more transparent. So we'll define a Riemannian metric on a complex manifold with a complex structure J to be Hermitian if J is orthogonal with respect to the Riemannian metric. Now, any complex manifold admits a Hermitian metric. You essentially hijack the Riemannian metric you get from a partition of unity argument and then produce the Hermitian metric via an obvious formula. So there's a certain class of Hermitian metrics we'll care about that behave a lot nicer than an arbitrary Hermitian metric. And these are the ones that happen to be Kayla. So I can produce from my Riemannian metric and complex structure J a two form given by feeding J into the first argument. The natural thing to do is, if you're given a two form that's non-degenerate, is to force it to be closed. That will give you an abundance of structure coming from symplectic geometry. And when we have a closed two form associated to our metric and complex structure J, then we refer to that as a Kayla metric, and the resulting manifold is said to support a Kayla structure. So the baffling thing about Kayla manifolds is that they exist in abundance. So for instance, if I look at the Forbenius-Studi metric on Pn, that will be a Kayla metric. Moreover, the Kayla property descends to complex submanifolds. So any complex submanifold of a Kayla manifold will be Kayla. And therefore, all projective manifolds are Kayla as well. Similarly, the Euclidean metric on Cn defines a Kayla metric. And so any Stein manifold, namely a complex manifold which holomorphically embeds into some Cn, that will also be Kayla. So in particular example of a Stein manifold is given by a pseudo-convex domain, so they're all Kayla. A rather striking fact is that for compact complex surfaces, so in dimension 2, the Kayla condition is topological. It's entirely specified by the first Betti number being even. And that comes out of some very elaborate theorems on the classification of Enriquez and Kadira. But one corollary of this is that the Hopf surface S1 cross S3, which is a compact complex surface of dimension 2, doesn't support any Kayla structure. Should add that I have broken my rule here, which is that every time I give a talk, I try to give a highly non-trivial example to keep everyone interested. And I wanted to produce an example of a Kayla manifold that's non-compact, that doesn't admit any complete Kayla metric. Such things exist, but I ran out of time. So in the next talk, that's one I'll present. This one is perhaps a little less well known, but will play a role in the subsequent developments. So this is a very important class of compact Kayla manifolds, and they're called Kadira fibration surfaces. They were introduced by Kadira in the 60s, I believe. So we'll define P from X to S, as in the beginning of the talk, to be a surjective holomorphic submersion. This time we'll assume it's also proper, so the fibers are compact. It's a surjective holomorphic submersion on to a compact Riemann surface of genus bigger than or equal to 2, with fibers being curves of genus bigger than or equal to 2. So we got a hyperbolic base and hyperbolic fiber. But one of the key properties that defines the Kadira fibration surface is that the fibers are not all biholomorphic. So there is holomorphic variation in the fibers and the complex structures non-trivially deforming. Okay, so we saw that there was a relation between the sectional curvature and products. That was in Priceman's theorem. But if I want to understand the behavior of complex manifolds as they're deforming, or the deformations of complex manifolds, the sectional curvature is not the appropriate curvature constraint, because that's purely a Riemannian invariant. It's not got anything to do with the complex analytic structure a priori. So the appropriate replacement to discover that, we'll suppose for simplicity that M, G, and J defines a Kayla structure. So the associated 2 form coming from feeding the complex structure into the metric is closed. If I complexify the Riemannian curvature tensor of the metric, I'll get a quadrilinear form on the direct sum of the complexified tangent bundle and its conjugate. And I'll discover that the only non-trivial components of the complexified Riemannian curvature tensor are given by U V bar W Z bar, where the the V bar and Z bar are the conjugates of V and Z respectively. Now with the sectional curvature, I feed in 2 vectors. So the appropriate Hermitian replacement here would be to feed in 2 vectors, but the appropriate thing I would discover would be this holomorphic bisectional curvature, which is given by U bar V V bar. If I was to express this in terms of the eigenvector decomposition, that comes from the splitting of the complexified tangent bundle, the Bianchi identity, when I write things in this way, would show me that this natural Hermitian replacement of the sectional curvature is actually a sum of two sectional curvatures. So in particular, this holomorphic bisectional curvature is named accordingly because it is a sum of two sectional curvatures. I should add that if it's not Kayla, the understanding between the bisectional curvature and the sectional curvature, even of the same connection, is not very well understood. But in the Kayla case, since the bisectional curvature is a sum of two sectional curvatures, the bisectional curvature is obviously weaker. But from the complex analytic viewpoint, it is the most restrictive of curvature constraints, aside from the sectional. For instance, in the positive case, we have this theorem of Mori and Xu Yao, which says that a compact Kayla manifold which admits a Kayla metric of positive holomorphic bisectional curvature has to be biholomorphic to Pn. The idea is to actually use this curvature constraint to show that the Kadira embedding is actually a biholomorphism. So it's an extremely rigid, it's an extremely constraining curvature condition if you assume a sign on the bisectional curvature. On the other hand, it's weaker than the sectional curvature as illustrated by this example of Mosen, which is very recent, 2018, this paper came out, where he produced an example of a compact, simply connected projective manifold with negative bisectional curvature. So compact, negative sectional curvature, if that was simply connected, that would have to be diffeomorphic to Rn by karatan Hadamard, so there would be a contradiction. So such manifolds can't admit metrics of negative sectional curvature. So from the point of view of Anderson's theorem, which showed that the total space of a vector bundle over a negatively curved Riemannian manifold has a negatively pinched complete Riemannian metric. The corresponding formulation in the complex analytic category would be to look at a holomorphic vector bundle with the base admitting, let's say, a Hermitian metric with negative bisectional curvature, but you could take it to be Kayla. And one could ask whether the total space admits a complete Hermitian metric with negatively pinched bisectional curvature. This would be the complex analytic incarnation of Anderson's theorem. It turns out that this isn't possible due to a result of Fangyang Zheng, where he shows that if you have a product complex manifold with one of the factors, let's say X, being compact, then you can't find a Hermitian metric, not even an incomplete Hermitian metric, with bisectional curvature bounded above by a negative constant. Now, the argument that he uses extends an older result, or an argument used to prove the following older result of Paul Yang, which says that if we have a holomorphic fiber bundle with the fiber being compact, then the total space does not admit a complete Kayla metric with bisectional curvature bounded above by a negative constant. Now, to really appreciate this theorem, we need to have in mind the following theorem of Fisher and Grout, which tells us that holomorphic fiber bundles, at least for compact fibers, represent the trivial case in terms of deformations and moduli, in the sense that if we have a holomorphic family P from X to S of compact complex manifolds. And the fibers are all biholomorphic if and only if P is a fiber bundle. And so as a consequence of this, we're able to, well, in my opinion, the right way to formulate Yang's theorem is the following corollary. So if we have a holomorphic family of compact complex manifolds, if the total space admits a complete Kayla metric with negative bisectional curvature, then one has to have non-trivial holomorphic variation in the fibers. There has to be some level of deformation. Now, one cannot relax this to some kind of asymptotic decay or non-positivity of the bisectional curvature. The bisectional curvature really does have to be bounded away from zero. So for instance, some time ago, Klembeck showed that there's a complete Kayla metric on Cn with positive bisectional curvature. Seshadri then essentially showed that the signs could be flipped. And so in particular, there's also a complete Kayla metric on Cn with strictly negative bisectional curvature. But it's not bounded above by a negative constant. So this leads to the following conjectural picture, which I propose, which is that if we have a holomorphic family of complex manifolds, not necessarily compact complex manifolds, and the total space admits a complete Hermitian metric with negative bisectional curvature, then F is not holomorphically locally trivial. So there has to be some non-triviality in the deformation in this sense. Now, the following result really kind of brings this home, showing that although the converse should not be true in general, there seems to be some evidence for it in the sense that if we look at a Kadira fibration surface, so remember that's a fibration with hyperbolic curve over a hyperbolic base with non-trivial variation there. Kadira fibration surfaces are defined by having non-trivial variation. Then one can actually produce a Kayla metric with strictly negative bisectional curvature on the total space. And the argument is actually quite nifty. The argument is to show that if you have non-trivial deformations, you get a map into the moduli space. And then on the moduli space, you have this Bay-Peterson metric of negative bisectional curvature, and you can pull that back to the total space, which I think is a tremendously useful idea. Now, let me finish here by posing the primary application of the conjecture. This is the main question of interest that I think this perspective should be able to bring light on. And it was raised by Mach at least more than 20 years ago, which was whether the bidisk, the simple example we started with of trivial deformations, the simplest example of a disk vibration we could come up with, does the bidisk admit a complete Kayla metric with bisectional curvature bounded above by a negative constant? Now, given the conjecture, no, it doesn't, it shouldn't, but it still remains open. And I think the right way to approach it should be to view it as an example of a disk vibration and then prove the more general statement. I think I'll stop there. Thank you.
Thanks, Kyle.
Yeah, thanks very much. Yeah. Yeah, I think that lived up to your title.
Yeah, it's I should stress, this probably may not come across very clearly. The theorems are not put in a coherent narrative at all in the literature. All the results kind of were viewed as generalizations of Priceman's theorem. This, the way I presented it probably comes like, oh, this is obvious, you know. Of course, it's the way to look at things, but that's definitely not the case.
Right, that's usually the way it goes. The picture emerges later.
Yeah.
Yeah. Does anyone have any questions for Kyle?
Or answers or solutions or
A possible sort of intermediate situation between the Riemannian and complex ones is something like two positive flag curvature, which I think includes your holomorphic bisexual curvature. It's be the condition that if you fix one vector, then the sum of any two sectional curvatures on planes that contain that direction would be positive or negative or whatever your condition is. So this would be.
Is there a way that, like, to generalize Priceman's theorem or? Yeah,
I don't know. I've never thought about that. These sort of conditions people have played with Ricci flow, for example. It sort of behaves nicely in four-dimensional manifolds in particular, but
in the negative, like
no, positive in that case.
Yeah. Have people looked at two negative flag curvature or?
Not as far as I've seen, but who knows? Could be somewhere.
I think there's actually a number of generalizations of Priceman's theorem that are available given the argument I proposed here using harmonic maps. Makes it, you wouldn't get constraints on the fundamental group from the bisectional, but you should get constraints on the second homotopy group because you've got maps from S2 into your manifold, which would be the second homotopy group, not the first one. But I'm trying to realize whether negative bisectional is enough to get you any continuous map is homotopic to a harmonic one. I don't know if that's true.
Have you looked at the PIC sort of papers right back to McAuliffe Moore and things like that? I mean, he used PIC and harmonic spheres as sort of the heart of that story somehow.
Yeah. There's a lot of stuff, I was saying this earlier, that there's a lot of results concerning harmonic maps from Kayla manifolds into Riemannian manifolds, but I want the other one. I want it into a Kayla. I actually think I have an argument, but it's kind of roundabout in the sense I have to use exponentially harmonic maps. There's always one of those in the homotopic class. And then there's some estimate which you can dig up that essentially there's one line which uses the negativity of the sectional. And I think that can be replaced with the bisectional, but I have only thought about that for about 2 hours, so I'm not ready to claim any result yet. But yeah, no, I'll look into this, the McAuliffe Moore paper again and things like that. Yeah, it's a long paper, isn't it? Isn't it quite long?
Yeah, I think it is quite long.
Yeah. There's a number of these extensions due to like Yao and Blaine-Lawson and concerning, constraints on the homotopy group. Yeah, it's interesting stuff.
Any other questions?
Would you dare to relax it to holomorphic sectional curvature?
Absolutely not. That's definitely false.
Oh, okay.
Holomorphic sectional curvature has this property that it behaves very well under products. You take two negative holomorphic sectional curvature metrics, product will also have negative holomorphic sectional. It's not so nice for the bisectional. You'll get flat directions. Like a product of two genus 2 curves. compact genus 2 curves that will have a negative holomorphic sectional curvature metric on it.
Mm-hmm.
So, yeah. Completeness is also essential because you can restrict any incomplete metric of negative bisectional to the bi-disk, for instance.
Mm-hmm.
And that, yeah. So the conjecture is actually quite sharp in the sense that the assumptions really can't be relaxed much further.
Mm.
All right. Thanks again, Kyle, for a very nice talk.
Thank you.
Thanks for wrapping up the year for us and everything. And
My pleasure.
we'll, I guess we'll see everybody in the new year.
Great.